Hi everyone, I am Naganiraj from the Department of AIML. This presentation is about our mini project titled Decoding Digital Addiction via Device Gaps. This project focuses on predicting problematic internet use or PIU using behavioral patterns hidden inside missing wearable data. In this presentation, I will explain the problems and its motivation, scope and methodology, architecture and design diagrams, algorithms and implementation, followed by code segmentations, results, conclusions, and future work. Coming to the introduction, problematic internet usage is a serious mental health concern, especially in children and adolescents. PIU is not normal usage. It involves compulsive behavior that affects sleep, academics, and social life. Studies how strong associations with ADHD, anxiety, and autism spectrum disorders. Currently, PIU is diagnosed using questionnaires which are subjective. Our project introduces ComplaintsNet, a novel system that predicts PIU using wearable sensor data, specifically when the device is not worn. Coming to the statement problem, existing diagnosis methods depends on parent-child surveys, which suffer from underreporting by children, lack of awareness by parents. Another major issue is by actigraphy blind spot. Most systems treat missing wearable data as an error and simply delete it. This causes survival bias, where the most severe cases, children hiding devices at night, are removed from analysis. Our objective is to treat missing data as meaningful behavior, not noise. The scope of the project is focuses on complaints phenotyping, analyzing how users interact with devices, not just physical activity. Improve diagnostic uh, objective by eliminating reliance on biased self-report surveys, targeted audience, pediatric clinicians, mental health researchers, healthy brain network example, and school-based screening programs. Deliverables: a trained and validated complaints net model achieving 0.502 QWK. QWK stands for quadratic weighted kappa. A classification framework identifying three novel phenotypes: the escapist, the disorganized, and the sensory avoider. The system predicts PIU severity objectively and identifies three behavioral phenotypes. And these are the three. Okay. Coming to the next slide, we'll be focusing on data and limitations. We use the Healthy Brain Network dataset here. Healthy Brain Network stands HBN, short form of it. With around 4,000 pediatric participants, we have 4,000 samples of data in that Healthy Brain Network dataset. Primary inputs are actigraphy, non-wear matrices, and battery telemetry, rather than standard activity counts. Pre-processing involves extracting behavioral complaints vectors to characterize missingness. Limitations of this are indirect measurement, dataset specificity, class imbalance, model generalizability. Performance may vary if applied to different age groups or devices with different battery characteristics. Medical expert validation. The identified phenotypes are theoretical constructs derived from data. They require further validation by pediatric physiatrists to ensure clinical utility. The transfer-based architecture requires significant GPU resources for training compared to traditional tabular models. Methodology. The methodology has five main steps like data collection, pre-processing, model development, system development. In the first step, we will be collecting data from HBN, something, Healthy Brain Network. The first step is utilizing the Child Mind Institute Healthy Brain Network dataset, which contains high-resolution actigraphy data for 4,000 pediatric participants. This dataset serves as the foundation to train our model to predict the Severity Invariance Index (SII). Data preprocessing. Unlike standard approaches that remove errors, our complaints vector extraction engine CVEE processes raw data telemetry to engineer behavioral features. This involves extracting specific markers like battery neglect, slope, nocturnal disconnect index, and generating binary non-ware masks. Model development. We will develop a hybrid transformer model capable of decoding missingness patterns. Okay. This architecture integrates soft dynamic time wrapping DTW for unsupervised phenotype clustering and a transformer based missingness encoder that uses self attention to predict PIU severity without data imputation. System development. We will design a clinical screening interface that allows practitioners to input raw active graphite files and receive objective risk assessment. The system will categorize patients into behavioral phenotypes to guide intervention strategies. Next will be our CVW explanation. Complaints vector extraction includes integrating raw actigraphy telemetry, gathering behavioral standards, selecting the non-ware monitoring locations intervals, installing feature fusion for multi-model signals, calculating, aggregating, and interpreting complaints vectors. It detects battery neglect, nocturnal device removal, micro removals, sensory avoidance. Hybrid transformer modeling includes collecting the healthy brain network dataset, choosing a modeling tool like soft DTW and transformer. Building a strong missingness aware model, simulating scenarios, analyzing results via five-fold cross validation, implementing the improvements for PIU prediction. Next will be our architecture and diagram workflow. The architecture starts with raw sensor data. CVE extracts behavioral vectors. DTW clusters daily patterns. The transformer predicts PIU severity. Final output is the severity invariant index. Next we'll be going through UML diagrams. This is our first use case diagram. This use case diagram shows how users and admins interact with the system. The next will be our class diagram. The class diagram represents the system object oriented structure. This is the overall structure of the class diagram. Next will be our sequence diagram. A class is a representation of an object, and in many ways it is simply a template from which objects are created. Classes form the main building blocks of an object-oriented application. Although thousands of students attend the university, you would only model one class called student, which would represent the entire collection of students. This sequence diagram shows end-to-end prediction and feature extraction flow. Next will be our algorithms. This is our sequence diagram. This is our class diagram. Okay. This sequence diagram 3 estimates between phenotype and modeling sequence. Next, coming to the algorithm. The project uses following algorithms. The complaints vector extraction algorithms used will be complaints vector extraction engine, an engineered algorithm that transforms raw telemetry including battery voltage, ambient light and physical agitation into multidimensional behavioral features, missingness as behavior paradigm, a novel logic that treats device non-ware periods as primary signal rather than noise, allowing for the detection of strategic, concurrent and executive. It is the basic model that is optimized for ordinary GPU. Soft DTW K-means clustering, a module utilizing dynamic time wrapping with Sokovu Chiba constraints to group daily 24-hour complaints interpretable phenotypes like the escapist and disorganized. Transformer based missingness encoder, a four-layer deep learning architecture that directly processes binary non-ware masks into long-range temporal dependencies in patient. Multi-head self-attention mechanism used within the transformer to automatically identify and weight critical time of the day patterns that are predictive of internet use severity. Consistent rank logits, an ordinal classification head that measures the predicted severity invariant index, follows a logical progression, improving the accuracy severe case detection. Quadratic weighted kappa optimization, a specific scoring algorithm used during training to minimize the distance between predicted and actual impairment levels, targeting a 12 to 18% improvement over standard baselines. Hardware and software selections would be sensors and computing frameworks, trial accelerometer, ambient light sensor, capacitive, capacitive wave sensor, battery telemetry to monitor exclusive device maintenance. The computing frameworks would be Python based deep learning stack, PyTorch for transformer architecture, TSLN for soft DTW clustering. Implementation would be done using Python libraries like TSLN and PyTorch. The project includes feature engineering scripts that calculate behavioral indices from missing data. We train the ComplaintsNet model using the Healthy Brain Network dataset HBN, which is nearly almost 4,000 data samples. The CVEE model extracts phenotypic signals from non-where periods previously ignored by standard pipelines. The model categorizes participants into one of four SIS classes based on their complaints topology. Coming to the important code segmentation, the this function extract complaints vector defines a function that extracts behavioral features. The bad features measures how often charging is neglected, and the nocturnal disconnect index will measure detects devices removal during night, and micro removal frequency captures frequent short removals. The sensory rejection vector identifies discomfort based avoidance. And next, coming to the next function, that will be temporal clustering module. And next would be our transformer missingness encoder. Self-dot embedding this line, I would convert input to model dimensions. Self-dot transformer is used for capture long range temporal patterns. Self.SI predicts ordinal severity levels. And next, coming to the end-to-end prediction pipeline. This pipeline extracts complaints vectors, identifies phenotypes, runs transformer inference, outputs PIU severity score. This would be our output. We'll be running all these test cases. This would be our expected result, and we'll be matching it with the actual result that we have got. We'll be comparing these both expected result as well as actual result to estimate whether the model passed or failed in that probable test case or not. These are our test cases for these are our feature components, and this would be the description for each of the feature component, expected output for each of the feature component, and the test result whether it is pass or fail. And the result would be in the form of accuracy F1 score and quadratic weighted kappa. The accuracy of the model would be probably around 88%. F1 score is 0.86 and the quadratic kappa is around 0.51. Conclusion. Coming to the conclusion, missing data is not noise, it is behavior. ComplaintsNet successfully predicts PIU severity using device non-wave patterns, enabling faster and more objective diagnosis. Future work. In future, we plan to integrate clinical notes and qualitative behavior data to further improve early PIU detection. Thank you.